It is my pleasure to welcome you all for this course on CFD. We are now into the module 3 of this week. So far we have done different approximation method, introduction about finite volume, finite difference, finite element method. Then we talked about properties associated with numerical scheme, mainly 3 properties: conservativeness, transportiveness, boundedness. Today's class will particularly talk about analysis of numerical scheme. There are again 3 aspects: consistency, convergence and stability. Particular theorem called Lax Equivalence Theorem that relates or connects all the 3 aspects while doing the numerical analysis. We will talk about these aspects in detail with example. Then it will be followed by explanation by taking different model equations. While doing CFD, approximations are made at different stages, and you get error arises due to these approximation. First step in CFD is computation modeling of a physical problem. Either we take a physical problem in toto, or we simplify the physical problem and then solve. So, in any one of this stage there is a possibility some assumptions are made, or there is a error in the conversion of computation modeling from physical problem. Second aspect is appropriate choice of boundary condition. Again, if a ill-posed boundary condition may result additional error. There is also possibility that you have computationally modeled properly, there is a problem in coding. So, you may have index, for example, I at j replaced with j and I. In such problem you may not be able to identify so easily. The program may run, but it may give wrong results after some time or after some iteration. So, one has to go back and check the code, and it is possible to debug and fix the code for correct coding. One more type of error is due to numerical approximation. There are 3 possibilities. One is truncation error, other one is a round off error, the third one is a discretization error. So, we will now focus mainly on this numerical approximation, error associated due to the numerical approximation. So, round off error is a number of significant digits considered. So, we know there are a lot of mathematical operations, subtraction, addition, multiplication and division, and in each of these arithmetic operation we handle numbers, and number of digits, significant digits considered after the decimal makes a difference in the solution. So, there is something called as single precision. In this we usually consider 8 digits after decimals. If someone decides to have higher accuracy, then you go for double precision, where we consider 16 decimals after 16 digits after decimals. So, there is a repeated calculation in terms of iteration or in terms of unsteady calculation, and over so many nodal points in a computational domain. So, though this appears, this kind of error appears very small, over cumulative this error will affect the results. The next important error is a truncation error. This is resulting by considering or neglecting leading terms while writing finite difference approximation. Now, there is a third error, what is known as a discretization error. This is a numerical error without considering the round off error. So, this truncation error, we mention how many or what term you are considering while writing the finite difference form of governing equation. So, you can neglect or you will consider up to some terms in the expansion, then you will neglect the remaining terms. Remaining terms can be odd order or even order. So, accordingly the error can be two types. One is a dissipative error. Here the leading neglected term is of odd order. Now, this also behaves like a viscosity. So, you know in basic fluid mechanics viscosity helps in diffusion. So, this dissipative error where you are neglecting leading term, and if the leading term is of odd order, then it functions like a numerical viscosity or artificial viscosity, but that helps in smoothing the problem. On the other hand, you may not get very peak or accurate results. The second type is a dispersive error, where the leading term, neglected leading term is even order term, and that results in what is known as overshoots or undershoots. So, you may have a solution with wiggles. Now, let us get explanation of these two type of error with some illustration. So, there in this figure what you see, there are three curves. Now, there is a black line which is going like a step function, and that is the expected solution or exact solution obtained by analytical way. Then if you have solved that equation with a leading neglecting term as odd order, and we mentioned it is a dissipative error, and you get a solution which is represented by the red line here. So, you see here it is smooth ends, and you are not able to get the peak here, or you are not able to get the peak here. It connects very smoothly without any problem. Of course, you can increase the leading term. For example, instead of first term you can take the second term or third term, then you may have a slightly improved solution, but still it never captures the peak. That is a property associated with the dissipative error. The second error is a dispersive error, and that is due to leading even order term, and the solution obtained will exhibit wiggles, that is overshoots and undershoots. So, you can see here light blue color, and that is a type of solution you will get. So, you can see up and down, then and so on. So, you have a problem either because of the dissipative error or because of the dispersive error. Now, we will try to get explanation of this from finite difference formula. So, we already did how to obtain forward differential scheme for the first derivative, and without going to the steps in detail, we write down the final expression here. So, dou f by dou x is given like this. Now, you have considered only the first term, the remaining terms are not considered. So, this is a neglected term, del x 1 del x to the power of 1 by 2 factorial dou squared f by dou x squared and so on, and followed by many other terms. So, this is a leading term that is not considered, and this is of odd order, and we mentioned this is a dissipative error. We also learnt how to write the same first derivative by central difference formula, and you get after simplification we are interested only in the dou f by dou x. So, we rewrite. So, dou f by dou x equal to like this, and you observe this is a leading term which you are not considered, and this leading term is of even order, del x squared is of even order, and that results in what is known as a dispersive error. So, the leading term if it is odd order, it will be dissipative error. Leading term if it is of even order, it will result in dispersive error. You get a smooth solution, but you will not capture the peak. In the second case, you will get a wiggles, but it may be accurate. So, there is a thought, why not we combine both, that is you take advantage of forward difference or backward difference and central difference. So, such a scheme, combination of both is what is known as a hybrid scheme, and people use that also to get solution. Next, we go to the analysis of discretized equation. We mentioned there are three aspects, one is a consistency, second convergence, third stability. Definition of consistency, it defines the relationship between differential equation and a discrete formulation. So, we have a original or a given PDE, then we rewrite or we replace that PDE with a discretized and we get a discrete formulation. Now, whether the discrete formulation actually represent the original PDE is a question, and that property or that condition is what is known as a consistency. So, it is a condition on structure of the numerical formulation. Second aspect is convergence, which connects the computed solution to the exact solution of the differential equation. So, what scheme you are using and how it is convergent, that information is obtained or analyzed by the property or aspect called a convergence. Third one is a stability. It establishes a relation between computed solution and the exact solution of the discretized equation. This puts a condition on behavior of the numerical scheme. So, in next few lectures we are going to get a definition and explanation with the model equation on these aspects, consistency, convergence and stability. There is a particular theorem called Lax Equivalence Theorem, which connects or relates all these three aspects, consistency, stability and convergence. The theorem reads like this: for a well posed initial value problem and a consistent discretization scheme, stability is a necessary and sufficient condition for convergence. To get some more explanation on this theorem, for a time dependent initial value problem, if you analyze the consistency and if you analyze the stability, then convergence need not be analyzed, it is satisfied automatically. So, when you are analyzing consistency, this leads to the determination on the order of the scheme as well as the truncation error. Similarly, when you analyze the stability, this tells on the frequency distribution of the error. So, if these two are satisfied or analyzed properly, then convergence need not be checked and it is automatically satisfied by this theorem. Now, one point that is to be noted, all these are applicable, particularly the stability is applicable for a linear problem, but in any practical situation all the problems are of nonlinear. Hence, to do analysis on stability of a particular scheme for a nonlinear problem, one can locally linearize and carry out stability analysis. Similarly, stability analysis cannot be applied near boundaries. Now, let us look at each of this in detail. First, we take consistency, which measure equivalence between original PDE and the finite difference equation which replaces the original PDE. So, when you replace the original PDE by a finite difference equation, as we know very well from Taylor series expansion, we consider only few terms and remaining terms are neglected, whatever the order of accuracy that you are deciding. So, that puts a truncation error, and if the truncation error goes to 0 as a function of delta t or delta x, which means if the length delta t and delta x goes to 0, the truncation error also goes to 0, then you recover from the finite difference equation the original PDE. If such thing happens, then the particular scheme is referred as consistent scheme. So, we know the Taylor series expansion. We take example of one dimensional temperature diffusion equation, and it is given here dou T by dou T, where T capital here refers to temperature, equal to alpha dou square T by dou x square. Now, we know by Taylor series expansion we can separately write for time derivative and second order spatial derivative. Any scheme we can write. We start off with forward time and central scheme. So, which is otherwise shortly referred as FTCS, forward in time, central in space. And for simplification purpose, we will take the coefficient alpha to be 1. So, it will be only dou T by dou T equal to dou square T by dou x square. So, if you substitute forward in time on left hand side, you get finite difference equation as T of I evaluated at n plus 1 time level minus T of I known from n level by delta T. This is forward in time, and as I mentioned yesterday's class, subscript I or j stands for spatial and superscript n stands for time. So, when you say n plus 1, it is forward in time minus n. So, you get forward in time. Now, on the right hand side we set central in space, but time is at n level. So, you can see in the expression superscript n appears, whereas subscript it is central in space. So, you get T of I minus 1 minus 2 T of I evaluated known at n and plus T I plus 1 n divided by delta x square. So, this expression we know already independently, we have learned by Taylor series expansion. Now, we are substituting them together. Now, what we do? We perform Taylor series expansion for each of these term, that is T I n plus 1, T I minus 1 n, T I plus 1 n. So, if you write the Taylor series expansion for each of the term, I am showing here for each of the term up to certain terms for each term. For example, T of I n plus 1 you can expand in time, forward in time, that is why it is n plus 1, and I have written up to 4 terms and the remaining terms are not written. Similarly, for all other terms, that is T of I plus 1 n, T of I minus 1 n, and you go on. So, all that we have to do is you substitute this expansion in the finite difference equation, in this equation, and we will see how to do that. So, if you substitute and rewrite or sum them properly, then we get expression like this, which is given dou T by dou T equal to dou square T by dou x square, and there are so many other terms, and these terms are coming from this additional term what we have considered because of the expansion. Now, while writing this also, we have considered only 2 terms, one corresponds to time, other corresponds to space, and whatever term are not considered, that decides the leading error term. So, this is of order delta t squared and of order 4 in space delta x. Now, I put all the things together. So, original PDE considered is given here, discretized equation is forward in time and central in space is also given here. Then upon Taylor series expansion for each of the term, substituting and rearranging, we get equation like this. Now, what do we do to understand consistency? Consistency definition: if delta t and delta x goes to 0, then original PDE should be recovered. So, we can understand that from this, if you make delta t going to 0 and delta x going to 0, then original PDE, that is appearing here itself, dou t by dou t equal to dou square t by dou x square. We get back the original PDE from the finite difference equation. Hence, this particular scheme, that is forward in time, central in space, for this PDE said to be consistent. So, one can analyze any PDE by this way. This is a very straightforward procedure. Now, we will take the next criteria, what is known as the convergence. So, this is an essential condition for any iterative procedure where to quit the calculation. Let us say we usually end up in an algebraic equation which is given here as A into phi equal to B. This is a set of equation that we will be solved. A is a coefficient matrix and phi is a variable which you are interested, and B is a known coefficient which is on the right hand side. Let us say you are doing iteration, then you get phi value previous level, you get phi value from the present level. The difference between the two is what is referred here as a epsilon, and this is evaluated for the current level. So, epsilon to the power of n is for the current level, and based on this we decide whether to quit the particular iterative procedure. So, one can set up a equation for residual. If you substitute epsilon into the solution matrix that we put, we replace phi by epsilon n, and then you get residue. Residue means the equation is not satisfied, some is remaining, and that is given by rho. Because it is evaluated at nth level, superscript n is given. There are many ways where you can use this epsilon to decide terminating a calculation. So, if you take a absolute, okay, so that is what is given here as a modulus of delta phi, which is evaluated for the case of 2 dimensional nodal location, that is why you get subscript here I comma j, and for the current level superscript n plus 1 is given. If the modulus of it is less than specified value, so one can specify error limit, say 10 power minus 5 or 10 power minus 7, some particular value for epsilon can be set whenever you are doing such a calculation, and once that difference delta phi at the current level n plus 1 and at all I comma j location is at less than convergence limit of epsilon, then you can say that we can terminate calculation at that step and proceed to the next stage. Okay. There are also other methods. For example, the first one I have written here, it is also possible to write based on summation of all the error, absolute error, and you say it is less than some value, prescribed value, and such is called L1 norm. Or you take summation, you take a summation of the square all the error. So, when you do square, there is no minus sign, automatically everything goes to positive, and you take a summation over the entire domain, and then you take a square root of it, okay. And that also can be used as a criteria less than prescribed value epsilon, and such is called L2 norm. And we will talk about this convergence criteria later class also with a different explanation. So, convergence is also decided based on previous value and present value. So, in today's class we talked about numerical analysis, particularly consistency and convergence with some example. We will see you again with another important aspect of this numerical scheme. Thank you.